Section 1, the first law of thermodynamics. It's all about the relationship between the energy trapped inside a system, the heat we give to it, and the physical work it does for us in return. The absolutely crucial point here is this simple equation. Delta U equals Q minus W. Angle delta, it literally just means change. So the change in a system's internal energy, its delta U, is simply the heat you supply to it, which is Q, minus the work the system does, which is W. Think of it exactly like a bank account. Heat is the money you deposit, and work is the money the system spends. What's left over? That's the change in your savings.
Let's look at a real example. A gas absorbs 800 joules of heat and performs 300 joules of work. Calculate the change in internal energy. Take a quick moment to visualize that. The gas pulls in warmth, it gets completely energized, and then it uses some of that newfound energy to push outwards and actually do work.
So let's solve this together step by step. Step 1, we write down what we know. Our heat, Q, is 800 joules. Our work, W, is 300 joules. Step 2, we write out our formula. Delta U equals Q minus W. Step 3, we simply plug in our numbers, 800 minus 300. And step 4, we do that simple subtraction. 800 minus 300 leaves us with an increase of exactly 500 joules for the internal energy. See? Pretty easy, right?
Moving on to Section 2, efficiency and entropy, which are governed by the second and third laws. Let's see exactly how machines use heat and what happens when things get incredibly cold. Whenever we build a machine, like a car engine, it operates on a very basic principle. The work the engine does, W, is equal to the heat it pulls from a hot place, the hot reservoir, which we call Q sub H, minus the heat it throws away into a cold place, which we call Q sub C. You see, no engine is perfect. It always has to throw some heat away. So the pure work you actually get out is just the difference between the heat it takes in and the heat it rejects. Imagine a really large, powerful machine. A heat engine absorbs 3,000 joules of heat from a hot reservoir and rejects 1,800 joules to a cold reservoir. Calculate the work done by the engine. Try to picture the heat flowing right into the engine roaring to life to do some heavy lifting, and then that leftover exhaust heat flowing right out into the cold. Okay, let's lay out the steps. Step 1. Our hot heat, Q sub H, is 3,000 joules. Our cold rejected heat, Q sub C, is 1,800 joules. Step 2. Our formula. Work equals Q sub H minus Q sub C. Step 3. We set up our calculation. 3,000 minus 1,800. And step 4. The final answer. When we subtract 1,800 from 3,000, we get 1,200. That means the engine performed 1,200 joules of pure work. Now, what's really fascinating here is how this introduces the third law. Look at these two temperatures in Kelvin, 40 Kelvin and 10 Kelvin. The third law tells us about entropy, which is basically a measure of randomness or molecular chaos. As we drop the temperature from 40 Kelvin way down to 10 Kelvin, the molecules in a substance drastically slow down. Their frantic dancing turns into this gentle, quiet sway. Because there's less movement, there's less randomness. Therefore, the lower the temperature, the lower the entropy. It's honestly a beautifully simple concept of nature finding perfect stillness. All right, Section 3, pressure, volume, and temperature. And we're going to kick this off with Boyle's law. Boyle's law is wonderfully intuitive once you get the hang of it. It basically says that if you keep the temperature of a gas exactly the same, its pressure and its volume are perfectly linked to each other. The formula is P1 times V1 equals P2 times V2. A gas occupies 5 cubic meters at a pressure of 200 kilopascals. If the pressure is increased to 500 kilopascals, find the new volume. Notice what's happening here. We're increasing the pressure pretty significantly, from 200 way up to 500. Because we are squeezing this gas so much harder, logic tells us the volume simply must shrink. Initial pressure P1 is 200. Initial volume V1 is 5. Our new pressure P2 is 500. Step 2. The formula is P1 times V1 equals P2 times V2. Step 3. We multiply our initials on the left. 200 times 5 is 1,000. So 1,000 equals 500 times our unknown new volume V2. To find V2, we just divide 1,000 by 500. Step 4. The answer is 2. Our new volume is exactly 2 cubic meters. It shrank exactly as we predicted. Section 4. Gas mixtures and amounts. Now we're looking at what happens when we literally pump more gas into a container, which is governed by Avogadro's law.
And this brilliantly illustrates the idea of proportionality. Avogadro discovered that if you keep pressure and temperature steady, the volume of a gas, V, divided by its amount in moles, which we call N, stays perfectly constant. So V1 divided by N1 equals V2 divided by N2. It makes total sense if you think about it. If you add more gas molecules, they're going to need more room, right? So the volume expands in perfect harmony with the amount you just added.
Let's look at this exact type of question. A gas occupies 8 liters at 2 moles. If the number of moles is increased to 5 moles at constant temperature and pressure, calculate the new volume. So we're taking the amount of gas from 2 moles all the way up to 5 moles. Because there's so much more gas in there now, the physical space it takes up, its volume, absolutely must expand.
Let's solve it together. V1 is 8 liters, N1 is 2 moles. Our new amount, N2, is 5 moles. Step 2, our formula is V1 over N1 equals V2 over N2. Step 3, let's plug them all in. 8 divided by 2 equals V2 divided by 5. Now, 8 divided by 2 is just 4. So to get V2 totally by itself, we simply multiply that 4 by our new 5 moles. Step 4, 4 times 5 is 20. Our new volume is 20 liters. See how smoothly that works? And finally, Section 5, the ideal gas law. This is the big one. This is where we bring literally everything we've learned today, pressure, volume, temperature, and amount, into one perfect, elegant master rule.
This is quite possibly the most famous equation for gases in all of physics, PV equals nRT. Let's break down these variables. Pressure, P, times volume, V, equals the number of moles, N, times a very special constant called R, times the temperature, T in Kelvin. Now, that constant R, don't let it intimidate you. It's just a fixed number that makes all the units balance perfectly. For liters and atmospheres, R is always exactly 0.0821. This one single equation completely connects the entire physical state of a gas.
The pressure of 2 moles of an ideal gas occupying 10 liters at 300 Kelvin. We have our amount, we have our volume, and we have our temperature. We just need to find the pressure. Even with a few more numbers, the process is just as gentle and easy as before. Let's lay out this step-by-step breakdown. Step 1, let's grab our givens. N is 2, V is 10, T is 300, and R is our trusty 0.0821. Step 2, we're going to arrange our formula to solve for pressure, P. So P equals N times R times T, all divided by V. Step 3, let's set it up. 2 times 0.0821 times 300 on the top, and we'll divide all of that by 10 on the bottom. If you carefully multiply that top row together and then divide by 10, there it is, 4.93 atmospheres, just by taking 4 completely different variables and applying one universal constant. Everything balances out perfectly to give us our final pressure. To ask you, if absolute zero is an entirely impossible destination, will our universe forever maintain a baseline of beautiful thermodynamic chaos? It's pretty wild to think about. Thank you so much for learning with me today.